So first we are going to discuss thermogravimetric analysis. So we have already seen what is a thermogravimetric analysis. It is the thermal analysis where mass of the sample is measured over time as the temperature changes. See, sometimes the temperature is maintained constant and then the weight change with time is noted. Sometimes the temperature is changed and then how the weight changes with the temperature is noted. So there are three variables, the temperature, time and the mass. Any one thing can be kept constant and the other thing can be followed. This is thermal analysis. So by this thermal analysis, we are getting information about so many physical phenomena. For example, phase transition, absorption, desorption, all these things are obtained. And then information about the chemical phenomena like chemisorption, thermal decomposition, or solid gas reactions, for example, oxidation and reduction. This information is also obtained from the thermal analysis. I have already told you in the class in a detailed manner what is a phase transition. See, the crystalline substances which are existing in more than one crystalline form, it is called allotrophy. Not only the crystalline substance, some hydrates, salt hydrates also we can observe the transition, phase transition. Say, for example, the hydrated sodium acetate and anhydrous sodium acetate or copper sulfate, anhydrous and hydrated. There is a phase transition between the hydrated form and the anhydrous form. So, thermogravimetry, there are three types. Number one, isothermal. Isothermal means which is done at a constant temperature, where the weight is a function of a temperature. And then quasi-static, static thermogravimetric, quasi-static thermogravimetry, and then dynamic thermogravimetry. These are all we have seen. And I have already told you for this, so you have to refer the book, The Principles of Instrumental Analysis by Skoog and Douglas, or Instrumental Methods of Chemical Analysis by Gurdeep or Chatwal. These are all the two books I am going to follow to teach this second chapter, second unit in your elective paper. Now, what is the principle of a TGA? The given substance is heated in a given environment, maybe in an air environment or nitrogen environment or carbon dioxide environment or helium or argon or any inert gas environment. So, the heating is done in a controlled rate. You cannot heat the substance as you want. What is this controlled rate? Suppose if you are rising the temperature should be risen in a particular rate, say 1 degree per minute or half a degree per minute, that should be very constant. That is the rate of a change of the temperature should be very constant. And then the weight change is recorded as a function of temperature or time. So temperature is increased at a constant rate and then weight is recorded as a function of temperature, or it is recorded at different time intervals. Thermogravimetric analysis, the graph we are getting in the thermogravimetric analysis is called thermogravimetric curve, or it is called a thermogram. So in order to carry out a very accurate thermogravimetric analysis, programmed very precisional balance is required. And this balance is called a thermo balance because the balance itself has to work at high temperatures. See, this is a model thermogram, where in the y-axis, the mass of the substance is taken, and in the x-axis, the temperature is taken. So, when you increase the temperature, initially there is no change in the mass. At a particular temperature, the mass change starts. It is called the initial temperature. The highest, the lowest temperature at which the mass change starts is initial temperature, and then the mass change is going on, it is continuing, and after a particular higher temperature there is no mass change observed, and this temperature is called the final temperature. So the substance A now becomes a substance B. So the substance A becomes a substance B, solid. So this is a model thermogram. Now you see, so this is what is actually repeated. In the y-axis, the percentage of mass or mass change is taken, and the x-axis temperature or time is taken, and the Ti is the procedural decomposition temperature, and the Tf is a final temperature. Ti, it is representing the lowest temperature at which the onset of mass change is observed, and the Tf is the temperature at which the process has been completed, and the reaction temperature is Tf minus Ti. It is that range where actually the reaction is taking place. So this reaction temperature depends upon the experimental conditions. So the experimental conditions play an important role in the reaction temperature. So when you change the atmosphere, the reaction temperature changes. When you change the quantity of the substance taken, then the reaction temperature changes. Sometimes the transition and other things are intensive properties. Actually, the transition temperature is an intensive property. Normally, transition temperature does not change with the quantity of the substance. Even if you take a small quantity or a big quantity, the transition temperature is going to remain the same. It is an intensive thermodynamic property. But certain other things will change with the mass also. So the what atmosphere in which the substance is heated, you may ask, sir, actually we are going to record only the mass change with the temperature or time. Then how does this atmosphere affect the thermogram? You may ask this question. You will be understanding this when we study the decomposition of the calcium carbonate monohydrate in air atmosphere and in carbon dioxide atmosphere. What happens? We can see in the next slide, next few slides, we are going to discuss why there is a change in the thermogram. Actually, the atmosphere in which the substance is heated plays a vital role. Now, so this is the TGA instrumentation. So the first important part of the TGA instrumentation is the recording balance, which is also called the microbalance. And the second one is called sample holder. So the holder in which the sample is kept. Actually, it is a crucible. Probably you are familiar with the usage of a crucible. In the inorganic or gravimetric analysis, you might have used a silica crucible or sintered crucible. Normally, these crucibles are made of platinum, aluminium, quartz, alumina, and graphite, stainless steel, glass, etc. And the furnace, we are using heating coils. Normally heating coils are used. Electrically, the substances are heated. So the furnace is a heating coil where the electricity is passed and the resistance coil is getting heated, and because of this heating, the temperature of the substance is increased. And there is one more thing, is the temperature programmer or controller or thermocouple. This temperature programmer or controller, it is designed in such a way that when you are programming the system to rise the temperature in a particular fashion, say, is this 41 is coming now? So you can program, and accordingly the electricity will pass through the coil so that the heating will be in a programmed manner. And then finally we have a recorder. Actually, this recorder is used to draw the thermogram. Thermogram is drawn using this recorder. You can simply look at the block diagram of the thermogravimetric analysis. Actually, here is the thermocouple. Thermocouple is the device which can measure the temperature accurately. This is the thermocouple. And here is the sample holder. This is the sample holder inside which the sample is kept. And then this is actually a closed environment where the atmosphere inside this chamber is adjusted like admitting the gas environment, and this gas environment is of the choice of the analyst. You can have an air environment or a nitrogen environment, helium, argon, or any other inert gas environment. And actually this is the furnace. Somewhere here the heating coil will be kept, which will be raised in temperature in a programmed, pre-planned manner. And actually this sample is measured using a very accurate balance, which is called microbalance. And it is not only a balance, which is a recorder also. So this recorder will record the variation in the weight, whereas the thermocouple will give you the variation in the temperature. So the time you can take any clock. So three important factors or three parameters based on which the thermogram is drawn, or the variation in the weight, which is recorded by the balance, and the variation in the temperature, which is recorded by the thermocouple, and also your time clock. So with these three variables, any thermogram can be completely drawn out. Now we are going to discuss the factors affecting the thermogravimetric analysis. So the factors which affect the thermogravimetric analysis are first the instrumental factors, and the second one is the sample characteristics. Regarding the instrumental factors, the first factor that affects the thermogravimetric analysis is the furnace heating rate. If you rise the temperature of the substance at a faster rate, then we are not giving sufficient time for certain very minute chemical changes to take place. So the thermogram will be accordingly with some missing components. And secondly, furnace atmosphere, I have already told you what will happen if the atmosphere is changed. And this particular point I have already told you that we will be discussing a later stage when carbon dioxide environment is kept or air environment is kept, how this calcium carbonate monohydrate thermogravimetric analysis gives a different readings or different thermograms. And the second thing is the sample characteristics. So weight of the sample, if you take a more amount, then the thermogram will be a little bit different. If at all, the difference is not much significant, there will be a, a difference. And the second one is a sample particle size. Why this particle size is affecting the thermogram? The particle size mainly speaks about the surface area, because the heating process, what is done in the thermogravimetric analysis, is a surface heating process. Suppose if the particle size is very small, then the whole substances, the assemblage will have a large surface area. Therefore, the heat exchange is highly efficient. But when the particle size is bigger, then the surface area is very less. So the heat exchange cannot be that much easily done with the bigger particle sizes. So the sample particle size and all the weight of the sample. So totally 4 factors, and 2 are pertaining to the instrument and the 2 are pertaining to the sample. So the instrumental factors to the furnace heating rate and the furnace atmosphere, and the sample characteristics, the weight of the sample and the particle size of the sample. So the next, the TGA curve of silver nitrate. Look at this curve. Initially, up to 473 degrees centigrade, there is no change in the weight of the substance taken. So you are already taken a known weight of the substance and it is kept in a furnace, which is heated. And then up to 473 degrees centigrade, there is no change in the temperature. Sorry, there is no change in the weight. And then at 473 degrees centigrade, the decomposition begins. So that is Ti, the onset of the decomposition of silver nitrate. And then this decomposition continues till 680 degrees centigrade, and after 680 degrees centigrade, there is no change in the weight of the substance. Suppose if your heating rate is much fast, what will happen? When the heating rate is much fast, even before half of the substance is decomposed, the temperature will go to a higher level. So the desired thermogram will not be obtained. Probably this will not be 608. By this time, it would have reached some 1000 degree. Even before the decomposition of half of the substance taken, it is because of the very high rate. So the rate of heating supposed to be optimum. So what decomposition is actually seen in the silver nitrate decomposition? Silver nitrate undergoes the liberation of nitrogen dioxide and oxygen, and the silver metal is deposited. So silver nitrate is a heavier, silver metal is lighter. So, and the nitrogen dioxide and oxygen are gaseous substances, so they do not contribute anything to the mass of the substance. So what happens? As the silver nitrate is heated, it goes on, and then the temperature comes down, and at 608, the reaction is complete. So this is the final temperature. This is the initial temperature. So the temperature difference between these two is the reaction temperature. And this is another some detailed block diagram of thermogravimetric analysis. The first one is the atmosphere control through by which you can control the atmosphere which is kept inside this chamber. This is the sample holder, and this is the recorder, balance control, recording balance. All these things are interconnected. And then there is a temperature sensor kept over there to find out the accurate temperature of the sample. And then the furnace temperature programmer is also connected to the furnace. And then this is the shaded portion is the furnace. So with all these things, we are able to maintain the temperature at a rate. We can increase the temperature at a constant rate, and then atmosphere is controlled, and then the recorders used here, which are able to record the time, the weight, the temperature. All these things are pulled out, and what we are getting out is the thermogram. Now, what are all the advantages of a thermogravimetric analysis? And what are the limitations of a thermogravimetric analysis? First, this involves a very small number of parameters or small set data. And the second advantage is it is a continuous recording. So you can study the material in the entire range of temperature. And third one is the value of the kinetic parameters is obtained. The limitations, the physical and chemical changes are not indicated. It simply speaks about there is some physical or chemical change. But what change has actually taken place is not revealed by the thermogravimetric analysis. And if at all there is no volatile product, so in the previous case we have seen the silver nitrate is decomposed and the nitrogen dioxide and oxygen are liberated. Here the nitrogen dioxide and oxygen are volatile substances, therefore they are escaping from the solid state, and hence there is a reduction in the weight of the substance. Suppose if the product is also a solid substance, then there won't be any change in the weight. Therefore, with no volatile product, no change in the mass is observed. So in such conditions, thermogravimetric analysis is of little use. And the last one, the applications of TGA. First one, the purity of the compound can be determined, because if you have a very pure compound, if it's a TGA is of particular pattern, then if you take another sample which shows a small variation from the TGA of the pure compound, by comparing these two you can find out whether the substance provided is 100% pure or not. So it is a qualitative step to find out the purity of the compound. And the second one, the determination of a composition of a complex mixture. See, by decomposition, suppose you are having a very complex mixture, that complex mixture is having two or more compounds which can decompose, then you can very easily find out what is the composition. Because if a particular composition is present, then the thermogravimetric analysis will give you the thermogram with a particular pattern of the TGA. If the same pattern is repeated in another sample, then that also contains the same composition. And another application is the study of a sublimation behavior of various substances. And then kinetics of reactions can also be followed, and a catalytic study can be done. Oxidative stability can be found out. Suppose if a substance is susceptible for oxidation, if the thermogram is recorded, then you can see the oxidation process. There will be a change. So the susceptibility, whether a compound is stable on heating in the oxygen environment or not. It can be found out using the TGA. And also analysis of the dosage form or the lifetime of a product or the decomposition limit of a product can be found out. Then residual solvent or the moisture, even the solubility of the pharmaceutical material or the effect of reactive or corrosive atmosphere on the material or the moisture volatile content on the materials can be found out. So these are all the various applications of thermogravimetric analysis. So you can see the thermogravimetric analysis of calcium oxalate monohydrate. Look at this calcium oxalate monohydrate. At 100 degrees centigrade, there is a mass change because the calcium oxalate becomes anhydrous calcium oxalate. The water molecule comes out. And at 400 degrees centigrade, carbon monoxide comes out. And then the oxalate becomes carbonate. And at 680 degrees centigrade, carbon dioxide comes out. And what you are getting is a calcium oxide. In all these things you see, in the first reaction, the water that came out was in the vapor state. So there is a mass change. And in the second stage, carbon monoxide is a gaseous, calcium carbonate is a solid. So again, there is a mass change. And in the third reaction, calcium oxide is a solid and the carbon dioxide is a gas. Therefore, another mass change. In all the three reactions, the one of the products is volatile. If these products are also solid in state, then this thermogram is of no use because the total mass is not going to change. Only the composition has changed, but the total mass is remaining the same according to conservation of mass. So in such situations, the thermogram recorded will not give you any useful pieces of information. But when any one of the product is volatile, when they are escaping from the system, then you are noting down only the mass of the solid residue. Then the thermogram will give you useful information. So this curve is a quantitative one. So because of its quantitative nature, the stoichiometric calculations can be done for any given temperature for any given system. So the next one is differential thermal analysis. This particular part we can see in the next hour.